Ladies and gentlemen, welcome to session 2A, Modeling and Enhanced Control. I would like to introduce our first speaker of this session. The first speaker is Miss Linda Åmand from Sweden. I'm closer. Okay. Our first speaker is from Sweden. She holds a master in environmental and aquatic engineering obtained from Uppsala University, and currently she is active at the Swedish Environmental Research Institute, where she works on energy efficient aeration control, and her presentation will be on energy efficient ammonia feedback control. This is to use this is forward.
And this is okay. Thank you for inviting me to speak in this conference. This talk will be on the topic of aeration control in the activated sludge process. As mentioned, I work at IVL, Swedish Environmental Research Institute in Stockholm, which is a non-profit independent research organization for environmental applied research. I also work in collaboration with Uppsala University, and Professor Carlsson is also the co-author. I do work a lot with ammonium feedback control in full scale, and at one point we asked ourselves, well, how energy efficient is actually ammonium feedback control? And perhaps we can have some help of the good models that we have in use today. And I will tell you today that ammonium feedback can actually have close to optimal performance. First, some brief introduction on ammonium feedback control. It's increasingly used today, both in the modeling world and in the full-scale world. And it's a means to change the dissolved oxygen set point in your basin based on an ammonium measurement, either in the outlet of your activated sludge process or in your actual process. Now you see the picture. There are good examples of when ammonium feedback control has contributed with energy savings in the range of about 5 to 20%. And you have the process down here with the two innermost controllers controlling the dissolved oxygen concentration with an airflow controller and a DO controller, and you have the supervisory ammonium controller as an outer controller. And the two innermost controllers are normally independent or individual zone controllers, and the ammonium controller is normally for each individual line. Now, all these three controllers are PI controllers. That's commonly the case, and PI or PID controllers are very commonly known in industry, and you have two controller parameters which you can tune, and I will talk a lot about them later on. You have the controller gain and the integration time, and the speed of this controller will be inversely dependent on the integration time. The objective of this study was to see, okay, what is the best variation in dissolved oxygen you can have over a day? And we tried to look at this from 2 points of view. The first one is using an ammonium feedback controller, and the second one is to ask for a mathematical optimal solution to the same problem, and then you can compare these two. When you deal with optimizations, you have to use some limitations on your process, which I will tell you about. And the first one is that we only consider repetitive daily load variations. No seasonal variations, no weekly variations, and this is for the optimization to be able to reach a steady state. Secondly, the treatment performance is measured based on a daily average of ammonium concentration. And whether or not this is a good limitation really depends on where you work. In Sweden, this is a good limitation, since we use average concentrations to assess compliance to the discharge criteria. So in this limitation, you don't consider time above discharge limit or anything. But in some cases, this is not really the system that you're working with. And finally, there is no aeration capacity limitations in these simulations, meaning the airflow that you ask for is the airflow that you get. So each controller performs as at its best, you can say. So now to the method. We use simulations in a modified version of the benchmark simulation model number 1 with a few changes. The first thing is that we only have nitrification, no denitrification. This is to speed up the optimization procedure. Secondly, we've added a model for the airflow rate taken from the BioWin model. And 2 plant configurations were used. The first one you see here, it's a completely stirred tank reactor. And this is used for optimization. And you have the airflow model, you have the DO controller, and you have the ammonium controller. But we also wanted to look at the plug flow case. So we had a 3-zone model too, where you have individual DO controllers for each of the zones. But this model was not used for optimization. And the reason is that you have to also consider the spatial variation of the airflow in this model, not only the temporal variation. In the previous model, you only have to deal with the temporal variation, and that's why it's possible to optimize as we set up the problem. We had 3 different influence to compare 3 different loads. The design load is this one, and it's based on the German ATV standard. And you also have the low-loaded situation and the high-loaded situation. And the inflow, the amplitude of the inflow increases with the load, so to speak. So now to optimization problem. The objective was to find the daily average airflow rate, which is minimal for treating ammonium to a certain level based on an average. And the reference case for all our scenarios is a constant DO controller. The first method, as I mentioned, was the dynamic simulations in the benchmark simulation model with modifications. Now, if you want to try to find the best ammonium controller, what do? Well, normally when you have a PID controller, you say, well, I choose this tuning rule. And the tuning rule says that, well, you will get a stable controller and you will try to follow this set point. But in this case, we are looking for an average effluent concentration. Perhaps we don't need to track the set point. So instead of using a tuning rule, we simply picked a range of controller parameter settings for the controller gain and for the integration time and combined them and saw which one was best. All simulations, independent on controller settings, had the same treatment result as an average. Now you want to see how good is this, how good are these controllers compared to the optimal solution. And the optimization was performed in MATLAB, and it was set up to minimize the daily airflow rate and to track the same average ammonium concentration as the ammonium controllers reached. And after that, we're able to compare them. So, to our results. I'll first show you the dissolved oxygen and ammonium profiles for the 1-zone case. And as a reference, to the left you see the constant dissolved oxygen concentration, and the circles represent the optimal solution over the day. The bold black is the best ammonium controller, and you see that both the optimal solution and the best ammonium controller reduces the variation in ammonium slightly compared to the dissolved oxygen, the constant dissolved oxygen case. Now with the 3-zone situation, you do not, I'm not completely satisfied with this tool. Okay. You don't have an optimal simulation to compare with here, but you have a similar feedback controller as with the 3-zone case, but you can actually see the effect that the plug flow has on the ammonium profile, which has more of a plug flow pattern to it. Now, this is just one of the controllers that we tested, the best one. But how does this controller compare to all the other controllers that we tested? Well, this graph tries to show you this, and you will see a few versions of this, so I will try to explain it for you. On the x-axis, you have the variance of dissolved oxygen concentration, and this essentially represents the speed of the controller. The faster the ammonium controller, the larger the variance in dissolved oxygen. On the y-axis, you will have the average airflow rate, which is your measure of energy in this case. To the far left, you have the black square representing the reference case with constant dissolved oxygen concentration. No variance in dissolved oxygen, hence it's 0 here. And the variation or the variance of dissolved oxygen can be changed either by changing the controller gain or by changing the controller integration time. And if you follow one of these black lines, each one of these black dots here is one simulation. And if you follow one of these black lines, the controller gain is kept constant, but the integration time is decreased, meaning the speed of the controller will increase. If you jump between these black lines, you will increase the controller gain. So if you go downwards from this reference scenario, you will have a minimum graph here, where you have a minimum airflow rate at a specific variation in dissolved oxygen concentration. This minimum point is found by keeping the integration time as large as possible, meaning essentially a proportional controller based on the controller error of ammonium. So, how does this minimum point relate to the optimal solution? The optimal solution is not too far away from the best ammonium controller, and it actually shows up at a very similar variation in dissolved oxygen concentration. In this graph, or in the ammonium controllers, there was a quite high limitation of dissolved oxygen. We allowed it to go up to 3.5 milligrams. That is high, but we wanted to see the behavior of the controllers when you actually allowed it to perform. I will also show you the other loads. This is the result for the design load case. And here you have the same graph, but only the minimum graphs as before, but for all the 3 loads. And I see now that the gray here is very, very whitish. It's the same graph, but instead of having the airflow rate, to have the relative airflow rate compared to the reference scenario. And there are 2 things I want to show you about this graph. First thing, when the load increases, the variation, the amplitude of the influent also increased. So, with a higher variation in influent, the more gain you can have by using feedback control. And secondly, the optimal points here, the filled circles, they moved towards higher variations in dissolved oxygen concentration with a higher load, meaning that a higher load variation should be met with a higher dissolved oxygen concentration, which is intuitive. So, what happens when you try to limit the dissolved oxygen concentration in the ammonium controller to a lower level? This is the design load case again, and this graph is not very easy to look at, so we zoom in a bit. Now, we took the maximum dissolved oxygen concentration in the optimal solution and put this in as a restriction in the ammonium controller. What happens then is that these hooks here represent the simulations with the limitation of 2 milligrams per liter. And all these 3 versions here have different integration times. So what you can see here, if you limit the dissolved oxygen concentration, you come closer to the optimal solution. That's one thing. The second thing is that you can actually use more integral action in this controller and still be quite close to the optimal solution, which is a good thing, because in real life you do want integration not to end up with a steady state error. So using a limitation, you became less susceptible to you can become closer to the optimum and use other integration times. So finally, I want to show you the results from using a 3-zone simulation. And this is the design load, and it's a very similar pattern, but you see that the hook here, it goes deeper down from the original curve. This one also represents the maximum dissolved oxygen limitation of 2 milligrams. So you actually gain more in this case by limiting the dissolved oxygen concentration in the 3-zone case, and that has to do with the shape of the plug flow ammonium concentration. So to sum up the results, you have for the 3 different loads and the 1-zone situation, If you have a properly limited dissolved oxygen controller based on ammonium, you will gain about 2.4 to 3.4% of the daily airflow rate. And this is not too far away from the optimal solution, actually. The variation you should apply over the day is between, of the dissolved oxygen concentration is between 1 and 1.5 milligrams per liter, depending on the load. So, my conclusions: compared to using a constant dissolved oxygen controller, you can save energy by using ammonium feedback control, and you can actually reach quite close to the optimal solution. But it is important to limit the maximum dissolved oxygen concentration, and these results are valid for the case when you only look at daily variations in load, when you assess the treatment performance based on average concentration, and when you have an ideal aeration situation, so to speak. So, if we go back to the first question that we had, that we asked ourselves, how energy efficient is ammonium feedback control? Well, it's actually quite close to optimal performance. So, thank you for your attention.
Thank you for a very interesting presentation. Do we have questions from the audience? Can you state your name and ask your question?
I have a question regarding the different scenarios. You've compared different loads, different people equivalents, but if I see it correctly, the ammonium concentration and the influence remain the same. In practice, it could also happen that, for instance, during dry and rain weather conditions, you have more flow but with lower concentration. How would this affect your simulation results?
If you also have a variation of concentration, you mean? Well, I would say that if you vary the load, the combination of the flow and the concentration, that is what shapes the response in dissolved oxygen. Because what you have time to treat is, or what you don't have time to treat in the end, is what is actually your control error. So if you also have a higher variation in ammonium concentration or a higher load in the ammonium concentration, the control error of ammonium will increase in the end, and that would sort of be also affecting what dissolved oxygen you should have to meet that variation. That wasn't really perhaps the answer to the question, but... Yeah, I have done other simulations too apart from this, and the results are quite solid, not only depending on the variation, but also the level of the load, if you move it up and down. And if you end up with a situation where you have little ammonium left, you gain more by by lowering the dissolved oxygen concentration, which is the basic idea about ammonium control, really, and that effect also shows up in these simulations.
Do we have any further questions? Yes, please.
Sebastian Meyer. I was wondering, in the model, how do you limit oxygen in the controller?
You say that the ammonium controller should not reach lower than 1 milligrams per liter in this case, and higher than a certain limit. So it's the controller that has the limitation.
Yes, and if the controller reaches, for example, the highest point, how does it respond? Does it shut down the aeration completely, or is there a kind of relation?
The controller keeps the dissolved oxygen concentration at that highest level. So if it's 2, it will stay on 2 until the control error decrease.
So that's the set point of the small loop, which is...
Yes, the set point to the dissolved oxygen concentration controller is limited. Correct.
Okay, thank you. In view of the time, I would like to end this discussion and move on to our next speaker. Thanks again for the presentation.